Hello. I am pretty much using the same slides as I used for my thesis presentation, so please ignore my semester and everything else notation. So my project was generating reinforcement learning agents. The motivation behind this is in general, machine learning models, and especially these model-free reinforcement learning agents, are black box systems. Because of this, attempting to understand and explain their inner workings are done through post hoc analysis, which makes it difficult to do things like identify and correct misinformed trends, whether that's relying on an unwanted bias or ignoring possibly important outliers. Understanding the decision-making process increases trust in the agent's performance, both for the industries using it and for the public. Specifically, this project approaches one small aspect of explainable AI as a whole, which is it possible to extract useful information from an agent as it runs, rather than examining the decisions it makes after the process is run. To address this question, I utilized process mining techniques to generate workflows from event logs extracted as the trained reinforcement learning model ran, and attempted to recreate the decisions that it made as it ran via process mining. So to go over the basics of process mining, because I know it's sort of a side field of data science. It was originally used in business analytics to construct an end-to-end view of all the stages that an event goes through. These include decisions encountered, events observed, and it transforms data in the form of an event log, as seen here, let me see if I can, I'm supposed to have a little workflow of it. A visual workflow where you can trace the events end to end through the different states. The process mining workflow generated is really useful because you can identify things like potential bottlenecks or concurrency. So I'll quickly just go through how to interpret this Petri net, because I know it's sort of a jumbled mess right now. You can see the event log that I had up before. And so I have the first 6 cases traced through in blue. So you can see event 0, this is blackjack, is the different moves that the AI plays. So you can see the initial hand is 11, then the AI performed a hit action, got the 21. This is all for the event log 0. Hit on 11, got the 21, and then stuck to end the game. So you can see that's traced through in the event log 0 in sort of the middle blue workflow. And then you can sort of see how then process 1 got 19, decided to stick on 19, ended the game that way. So you can sort of trace through and see the steps that were taken for each event. The black squares are silent steps. They basically represent a point where you don't have to make a move. You can just move on to the next choice point. So I'll just quickly touch on the environments I used to extract data from. I just used a very simple OpenAI gem to get them up and running quickly. So I used Blackjack, Frozen Lake, and Taxi. For this presentation, I got the most useful and information data from Blackjack, but I will go over all of them. And all of the agents were model-free Q-learning agents. I'm not really going to go into detail about the training process here, but because it's not really the focus of the presentation, but I'm happy if anyone has questions. So the first environment is the simplest, it's Frozen Lake. It's literally a 4x4 grid. You can see the winning state in 15, you're trying to get to the present. And if you fall through any of the 4 holes in the ice, it ends the game and you have to restart. The one thing that's interesting about it is it has a slippery mode, which adds randomness, where you don't necessarily go where you want to go, which converts the model from a deterministic one to a stochastic one. Blackjack is modeled on the classic card game. The state information you have is the sum of the 2 cards that you're currently holding, whether you have a usable ace and one of the cards that the dealer has. There's two actions. You can either hit, which is to have the dealer give you another card, or stick, which ends the game. And then there's a few different end states. You can either win by getting 21, having more than the dealer, and under 21, or you lose if you go over 21 or have a lower score than the dealer. Taxi is probably the most complex of the three environments I used. Your goal is to pick up a passenger at one state and then drive through to the next goal state. The things that make it a little more complex than Frozen Lake, for example, is that it's time penalized, so you have motivation to find the shortest path. And you also have to obey traffic rules, which means that you can't cross solid white lines. You can only move through dotted white lines if you're trying to change a lane. So now I'm actually going to move on and talk about process extraction. The next few slides are all just going to be based on blackjack, just because if I went through all models and all of the different processes I used, it would be a much longer presentation. But so initially, I used just true process mining, which uses state information stored as just event ID, action, and timestamp. However, as you can see here, the very simple, purist expression of process mining didn't really generate anything too insightful. It only gives the most general information about how to play the game. You still get sort of the most basic rules of blackjack, which are that sticking ends the game and you can't hit after you stick, but it gives no insight into when you would like to hit or when you would like to stick. Attempting to remedy this problem of being too general with state information, I then added in full state information to the log. So I added in, for blackjack, the sum of your current hand, the dealer's hand, whether or not you had an ace. However, this quickly became unmanageable with large state action spaces like blackjack and taxi, where you ended up with a unique process trace for each event. And this sort of defeats the purpose of what I was trying to do, which was to extract generalizable rules rather than simply a decision tree that you would, blindly follow. My goal is to extract sort of the reasoning behind why you do things when you do things. So to this end, I moved into a partial state representation to sort of keep that generalizable rule system, but also be able to extract a little more meaningful information about what to do when you're in a certain state. So for blackjack, I just kept the sum of the current hand. So this shows multiple playthroughs that you can see sort of the lower cards that you'll probably hit on, to the middle cards that you might sometimes, and then you can see the end states where you've either got 21 and you end the game. You can either end when you have a card like 19, and then you can move through and end the game moving through the silent step, or if you've hit on a mid card and gone bust, then you can see those end states as well. So I'm going to touch on the specific algorithms I used when actually performing the process mining. So that's alpha miner, inductive miner, and heuristics miner. These are just three different mining algorithms. I use the PROM, process mining software, that has these algorithms built in to process my event logs using these miners and generate the workflows. Alpha miner was a good start, but it was very simplistic. So alpha miner works by looking at a start state and an end state and joining in the middle. And so when I had the incomplete state representation, it really struggled connecting those, the start and end states back together. So then I used inductive miner, which is a much better Petri net. As we've seen the past couple, you can actually interpret it. And so basically how that works is it detects splits in the event logs and builds a representation based on those splits. Finally, I used inductive miner, which wasn't quite as human readable, but still had some useful features, which I'll talk about later on. And heuristics net looks at the frequency of occurrences in the event log. So moving on to the process, the three different process models generated, you can see on the side over here, the how alpha minor struggled connecting those end states up at the top to the initial state, sort of in the middle here. The middle is inductive minor. This is one that I've shown previously. You can see the playthrough a lot more effectively. The one useful thing about heuristics minor that you can see here is really how it does reflect the frequency of different states, where the light gray is the least frequent states and the dark gray or black is the most frequent states. Frozen lake representation was pretty simple. So for the state representation, I just used the numbers on the grid from what I showed previously, 0 through 15. There's only one best path for deterministic frozen lake, and you can see it there. All three mining algorithms generated that same graph. But adding in the slippery element of randomness, you can see that it starts to look a little bit more like the blackjack Petri net. But you can still see sort of a reflection of the moves that you would make. You can see the end states over here. And it does give you a little more nuance into moves that you would probably take in a current state, even with that element of randomness. Also, it's nice to show that it works with the stochastic model as well as the deterministic one. Taxi was the most difficult state representation to decide on. I first used Manhattan distance, but that was too general. It didn't reflect anything about the goal states or the road rules. So for these workflows, I just used the current location of the taxi on the board, almost similar to the frozen lake grid. You can see I ran into the same problems with alpha minor trying to connect over here. I'll zoom this in a little bit more because it is a pretty large map to try and show on a slide. But you can see that it still is reflecting some of those really basic rules with respect to like the dynamics of how you'd play the game. For example, there is sort of a bottleneck here where the only place you can cross from the left-hand side to the right-hand side is this row. And you can see that in that choice point right there with the different goal states circled in blue. So if it's trying to go from one start state to a goal state, it has to move through the second row. With more time, I'd play around with the state representation a little bit more, but this was just a one-semester project, so I did not have a ton of time. Another thing that I would do if I had more time would be to have a person try and recreate the rules of a game with these workflows. And I would also try to extract rules and train a model based on those rules to sort of see if I could recreate the game based on the rules I've extracted from that workflow. Anyway, thank you. It was a very, anyone has any questions? Yeah. Yeah.
One thing that people often found is that like you can do quite well just using heuristics. I think
Yeah.
one of the things that I was really find out would be like, what is like the amount of money you would like make, you know, the best model versus a simpler like heuristic model.
Yeah, exactly. When is it like good enough? Yeah.
And I think one of the like things that's really different with this sort of stuff is like it's really important, but it's also like hard to quantify what like readability, like human readability is.
Yeah.
It's kind of like, well, we could sort of like if we have the best process extraction, probably perform the same
Yeah.
as like the model that was extracted from because it's so extensive.
Yeah.
Similar, but then it's like not.
Yeah.
Yeah, I guess that's a challenge that's like overcome here and then that.
Yeah. Works. Yeah.
Question. When you were working with the Petri graphs,
Mhm.
right? Did you observe sort of over time, generally, the graphs, as you sort of went through more and more states, did they become more complicated, or did simplicity start to emerge?
With more states?
Yeah.
Yeah, the graphs do. I mean, as you could sort of they do increase to the number of states. So like, here, let me go back to like one where I had like the full state representation, and this was only, I think this is just 10 playthroughs, but then if I tried to do full state representation for all of blackjack, I think that's like over 300 possible initial states. And so it essentially just created this, it would play through all of those initial states because I was doing, many tens of thousands of runs. And so it would increase proportionally in size with the number of possible states, which is what sort of drove that simplification of the state representation.
Okay, so it did sort of eventually become a little bit more simple.
Yeah.
Okay, interesting.
So the graphs are, correct me if I'm wrong, they're a graphical representation of the policy kind of.
Yeah, well, that's the ideal. The idea is that you're trying to sort of graphically represent a way that you could replay the policy if you wanted to. Like theoretically, you would be able to person down and learn the rules to blackjack by following through this, rather than just having a rote map that they would look at and be like, oh, I'm in this initial starting position, that means I should play this. They would gain a little bit of that nuance of like, oh, if I have a low card, maybe I should probably hit on that because that's what happens most of the time.
So you weren't generating them while training was happening?
No, these were all fully trained. Yeah.
What if you chose a programming source code as your representation, so that if your analysis produces a Python program that works, that'd be a more human readable representation?
What do you mean, like?
Instead of a graph, right? Have it right.
Oh, yeah.
Have the right code, and if the code is readable, then
Yeah. I mean, yeah, you could definitely do that. I mostly just use the graphs because, again, that was the output generated by these existing process mining workflows. But I could technically take that output and recreate it into another model or something like that.
So one of the things that's always really fascinating to me is that, like, if you look at the vector representations inside some of these DQ models, they have semantic structure.
Yeah.
So it's like, in space invaders, there will be situations where there are more like half the space invaders have been shot down.
Yeah.
Near states with less space invaders as well. So there's these semantic representations. So I think that one thing that was obviously done here just because of time was that all your courses in the state space were manual.
Yeah.
It just occurs to me that if you just took the vector representations of these state spaces, then clustered them, you might get something that's kind of natural. So you
Yeah.
get situations which is I kind of have a high card. And
Yeah.
dealer kind of has high numbers as well, and you do something different.
Yeah, for sure. It's definitely, this was sort of just it was a very short project. It was just sort of a very basic proof of concept. Can you process algorithms to generate something that you can use maybe? But yeah, definitely I tried it with Tetris. I did not have enough time to do that, but it was, I had some very interesting results on the event logs with Tetris, but it was just very messy and I didn't have pretty data in time. But you can use it with with larger and more complex events.
So if you had trained two models to play these games and one was really bad,
Yeah.
one was really good, you'd see totally different
Yeah.
patterns, right?
Yeah.
So you're showing not how the game works, but how this particular model plays the game.
Yeah, exactly. When I was initially trying it out, I did use it on the event logs generating when I was training my models, and the Petri nets generated were much more chaotic because they didn't have that same. Whereas like the Frozen Lake one, where it was I know how to play this game. This is the best path. There is no deviation from this path. Whereas when I was training it, you would see it sort of experimenting and finally coalescing on that best path.
Did you just do tabular Q-learning, or?
Yeah, for this, yeah. I did DQ for my Tetris one, but for these three, it's all just tabular.
Do you think if you had more time, this would scale more of an open-ended environment? Or?
Yeah, definitely. I mean, I think both the types of Q-learning models and also the process mining algorithms I used were very basic. There's some a probabilistic inductive minor that I think it's, you know, if I was able to adapt that, I think having the nuance of the most frequent paths is an interesting piece of input as well. So I think as you get bigger, you might need more complex process discovery algorithms. But I do think, I mean, I do think this is an interesting approach to explainable AI, and I think it can, I think you could use it on more general and less, you know, little tiny toy AIs.
Yeah.
Yeah, I was just thinking about like what interactions or like courses work for things like if you're playing chess, there's
Yeah.
always heuristics like, you know, knights on the edge are bad, or like you know, don't push pawns in front of your king and stuff. Like
Yeah.
It's interesting to see like in a richer scenario how you would like coarsen up enough so you can still get those kind of like rules
Yeah.
out of the systems.
I'm just thinking,
Yeah.
would it be like technically possible to just go from the policy in a deterministic way from the policy to the graph?
You could, but the whole point of this was that because it's a because it is the model-free reinforcement learning agent, I don't have the initial policy that I know, so I'm trying to see how the model has trained itself. You know, it's so yeah, theoretically you could just use the policy, but and obviously for something like this, I have a general idea of what the policy the model learned is. But the idea is if you had a larger, more complex model and you weren't really sure of the policy that it taught itself, and you were trying to sort of maybe identify incorrect or weak points in that policy that it trained itself, you would be able to identify that through these generated graphs. Because you are trying to basically map the policy and identify the weak points in that possible policy that it learned.
Okay.
Yeah.
Makes sense.
Yeah.
Well,
Cool.
thank you.
Thank
Well,
you.